Good morning. It is a pleasure to be here with you. We are going to try to summarize in 25 minutes or even less what we've learned about the redox aromas in the last years.
Bueno, vamos a ver, vamos a empezar por el principio. ¿Por qué llamamos reducción en general en el mundo del vino a algo que está relacionado con las moléculas de azúcar?
We call redox something that is related with sulfur molecules here, but remember that redox means really a chemical process of to gain electrons. I mean, it's not only with sulfur. It is with sulfur for us, but universally, redox are these such chemical processes where iron oxide loses electrons, and when it gains electrons, well, if a molecule is oxidized, then it loses electrons. If it's reduced, it gains electrons. So you can see the reactions that take place in a furnace. Oxidation is caused by oxygen, but what about reduction? Well, we need the concept of redox potential. The moment we remove air, the wine is going to tend to develop a negative redox potential, and therefore we will have the whole iron in the shape of iron 2+, if there has been a reduction of air. A reduction aroma is by definition an aroma that is formed or released when the wine is made more reduction. So, sulfur dioxide is very volatile. It is a gas, and it is, well, it's only formed during fermentation. It's a subproduct of the metabolism of wine. It is lost partly by CO2, and when the wine is resting without having any contact with air, it can reappear, especially in the wines that are having long alcoholic fermentations. Methanethiol or methyl mercaptan is a molecule associated with the cauliflower, the smell, the scent of cauliflower or rotten garlic. It is a very powerful smell or odor, and it is in the threshold of 1.5 ppb. The origin is fermentative, and it can be originated by catalytic reactions from methionine. Something similar happens here to what happens with H2S, the dihydrosulfide, and this can happen already in aging, not only in fermentation. But these compounds are normal part of metabolism of the yeast metabolism and fermentation. The moment there is a lack of nitrogen, the sources of nitrogen incorporation of yeast fail. Then there is an accumulation of sulfur, and it is expelled to the outside matrix of the cell in the form of H2S. So there is a deficit of nitrogen, which is the cause, a very well-known cause for this. There are other situations like cell stress or sudden changes in temperature or the lack of oxygenation at the beginning of the fermentation. This depends highly on the type of yeast to be formed. Every yeast is different, and there's also an inappropriate handling of the growing with lees. What do we do when we have a problem? We try to palliate it with oxygen, and we also employ a series of products containing copper salts in different forms. What happens? The moment we store a normal wine in the absence of oxygen, this is what happens. This is the H2S free content This is an accelerated aging, but the scale could be like 2 aging years. There is a continuous production of free H2S. This is unavoidable, but we have wines that are producing very little amounts and wines that are producing very big amounts. The differences between wines can be over a factor of 15, and well, there are some wines that are a real manufacturing plant of H2S. Any wine is going to produce like 5 parts per billion per year, if talking about red wines, and the white wines 8.5 ppbs per year. And this we must be prevented for this, because this is like this. As for maximum levels, we have found some wines with 30 ppbs per year and some wines with problems that were producing up to 70 ppbs per year. This is an accelerated process. This is the initial content, and this is the content that we expect this wine to have in a year time. See that here we have a family of wines that did not present apparently any problems. Some of them had been treated. They were having less than 1.5 parts per billion. Some other wines with light problems, some other wines with more serious problems, and here are some wines with very serious problems. See the evolution of them. Curiously enough, only 2 of these wines are commercial wines. They don't produce practically anything. There is other group that is producing between 5 and 10 parts per billion, but look what happens. Some wines that were not producing anything, here they are, after 2 years, they are producing 10 to 15 parts per billion, and here we have between 15 and 25 ppbs, and this green wine here, well, in green I mean, that is producing more than 25 ppbs over time, and this is a problem. So the increases normally are linear with time, but on average we have between 1 ppb per year in red wines and 1.7 ppbs per year in white wines. Here you can see that the differences are less intense, but you can see that some that we were having very low levels, they can form important amounts over time. And this is a very unpleasantly smelling wine. What can also happen during aging without air? Well, the moment there is lower access to oxygen, well, there is a process of spontaneous condensation of polyphenols that is giving electrons to the medium. We don't understand this, or why is this produced, but this is a true empirical reality. What have we learned? Well, in essence, what we are seeing and smelling is just the tip of the iceberg. Most of the H2S and the MESH are existing in 3 different chemical species that are balanced among them. The free forms, the complex forms with metals, and the oxidated forms where we have complexes with cysteine and glutathione. These free forms are the only ones that smell. The complex forms are complex with copper, iron, and zinc. And here the sulfur atom is reduced in -2 form, what we call the sulfide. And here the oxidated forms, the sulfur atom can be in disulfur or polysulfur form. These 2 forms are linked by a balance of complex formation, and this is linked by redox equilibrium or balance. This is overlapping the most important redox balances of the wine. We have here iron which is in its oxidated form, and the copper with the reduced form. And very importantly, we have here the balances of the mercaptans of the wine. I refer to the proteins that have H2S. I refer to glutathione and cysteine, and they can be in oxidated form with a disulfur bridge, and then or the reduced form. And these are majoritarian forms that are dominating the movement of these equilibriums or balances. And these mercaptanus here, the glutathione, can be forming complexes with metals. So let's see what happens. These are oxidated forms, and these are reduced forms. Here, sulfur appears as -2, no disulfurs, and iron appears like -2. And here, sulfur is as disulfur, and the iron is as iron 3. And what happens when oxygen is coming to the wine? Well, the first thing that happens is that iron 2 becomes iron 3. Iron 3 is a very reactive species and cannot coexist with these mercaptans. So the moment we have iron 3, it passes on to iron 2, and then it's removing one electron from the glutathione, and these forms are accumulating. This is, well, it becomes dragging or pulling the most complex forms, and the iron is being used up, so that these forms become metallic forms, and then they transform into oxidated forms. So after an oxidation process, we have moved from this phase to this other phase. So it is a chain reaction or chain process. In the reduction process, imagine that we have oxidated wine. What happens after this aeration process? Well, when we don't have oxygen, the opposite happens spontaneously. We don't know why. These electrons appear, and they are falling onto the sulfur, and this is accumulating, and it is going to react with the iron, so all the iron is going to be transformed into iron 2, and these oxidated forms are going to be transformed into complex forms first, but if the process continues, there will be an accumulation of these mercaptans, so it will get capture all the metals, and it will expel from these complex forms the H2S and the MESH. All this is related to the redox potential of wine, which is due to two chemical balances, the oxidated glutathione and the reduced glutathione, and what you can see here in the screen, we have the dominion of the iron 2 and the dominion of the iron 3, the dominion of the sulfur -2 and the dominion of the sulfur -1. This happens around 0 millivolts, and this happens around 100 millivolts. This is what we get when we have a very reduced wine, and this is what we get when we have a highly oxidated wine. Well, see what happens. This means that all the H2S that is having wine that can be under any of these forms is always the same. But it depends on what is the potential. We will have some forms or some other forms. So we will have free hydrogen sulfide, and we will be reducing the amount of free forms. The complex forms are having average potentials, depends on the copper amount, and then we will see oxidated forms that will appear. So at very oxidated potentials, we will never smell anything, but we will have all our hydrogen sulfide, which will be in the form of disulfur. And depending on the copper that we have, maybe we will not smell anything, and we will only smell when there will be very highly reduced potentials. More. In some wines, apart from this mechanism, and especially for methanethiol, for all wines, we have, apart from this balance, we have a continuous production system of hydrogen sulfide and methanethiol from the corresponding amino acids, and we know that it is a reaction catalyzed by metals. So, the one that has a lot of cysteine and methionine will know that this is going to happen. Well, we have a three-step strategy. We first measure the free forms, then the free forms that are complex forms, and then what will happen after spontaneous reduction of the wine. The free forms are measured here, leaving balance and measuring how many methanol we have. We add here a brine with sodium chloride, and we force the breaking of these complexes, and all these forms are moving onto or passing on to free forms, and then we will measure the amount of free forms and complex forms. And in the accelerating reduction form, we store the wine at 50 degrees for 2 weeks, and we will let the wine to get to the reduction area, and we will measure both complex forms and the most complex free forms. And we will measure the forms here at the redox potential and the complex forms, so that we will know this amount. And then we take the wine, we make it undergo an accelerated reduction, and we measure both the free forms and the free forms plus the complex forms, and we can interpret through the bars the trend of this wine. Here I show you some examples. The blue bars are the free forms. Out of the 6 wines that you can find here, only 5 were having a worrying amount of free forms. The orange forms are the complex forms. This one had a very low amount, but it is due to it's been oxidated. These are normal amounts, and this one has a very, very high amount. And these are free forms after accelerated aging. You see, the V2 is not giving away any levels, and here we have worrying forms. And finally, after the accelerated reduction, we have total forms, and you see here all wines having total amounts that exceed 40 ppbs, and in some cases it can even reach 200 parts per billion. What are the solutions? Well, we have good and bad news here. What about treatments with copper? When red wine with a certain reduction problem is treated with 3 different doses of copper as copper sulfate or with a commercial product, we see that immediate effects of the treatment or after the treatment are great, are very good. You see the control wine here, and the moment we add copper, the hydrogen sulfide disappears. What happens when this wine is aging or starts aging? This is the one without copper. This is approximately what would happen after 6 months of accelerated aging, and we see that this wine can even give away 30 parts per billion. And with copper, we are reducing the rhythm as the release rhythm, so that with a very low dose, after a year, we have not reached what the wine was producing spontaneously after 6 months. And with more doses, we would take 2 years in getting the same levels that the wine would get by itself without the copper. So the copper is delaying the process, but is not removing the species. It is only slowing down the whole species, the whole reaction. With methanethiol, the good news is that we have an immediate effect again that is very little dose dependent, and you will see what happens on the longer run. Well, the effect on a longer run is really small because methanethiol, the important thing here is the content that the wine can produce continuously, and you can see that after half a year, you see there are differences in the methanethiol levels, but after a year, there are no significant differences, and after 2 years, there are no differences whether there is copper or not, because the wine is going to produce more methanethiol by itself. And therefore, copper has an immediate effect here with removing the free forms of both hydrogen sulfide and methanethiol. However, these forms are not removed. They only pass to be transformed into more complex and oxidated forms, and therefore copper can delay everything 1 year, but it can have a collateral effect. And what about micro-oxygenation? Okay. This is what happens. This is the Redox scale of a wine that we have submitted to some micro-oxygenation processes. This wine has an amount of 80 parts per billion of hydrogen sulfide in the free, more complex form. And if we reduce it with the accelerated reduction test at 2 different times, we see that it releases up to 160 parts per billion. This wine was having a serious reduction problem. When we oxygenated it with at 3 different moments, we can see in the graph what we got. We reduced it, and it comes here again to the same initial status. This wine that received a similar dose comes back here, and this other wine, when we reduced it, comes back here and here. What do we have? The balance that I just showed to you. This is a sigmoid curve, and what we do with oxygen is just moving from one side to the other. We are not achieving in touching the total hydrogen sulfide amount or content that we have in the wine. So, oxygenation has a very little role in removing these compounds. This reaction of sulfides that we all chemists thought that was happening with quinones, we don't have any evidence that this reaction is being produced in the wine. Sulfides pass on to these sulfur forms, and then they are protected. You have to remember that during fermentation, oxygenation does have a key role because it gives electron capture that avoids the yeast to force the production of hydrogen sulfide. We don't know how, but this is what happens. As a result, only the cork has a provable effect. What we can do here, apart from impeding fermentation, we can only use corks with different permeability to oxygen, and this, well, the conditions of our wines are going to have a very important influence, but we do choose, if we do choose corks with a high permeability to oxygen, we're going to be in the yellow zone, and then this wine is not going to be long-lasting, but it is never going to have a problem with oxygen. But if we have a cork with an average, moderate permeability to oxygen, we will be in the bluish area. And if we have an anoxic cork, then we will have this gray area. We will be in the gray area, and the wine will accumulate these processes. These compounds are in free, complex, and oxidated forms that are totally balanced. And it depends, this balanced state depends on the redox potential of the wine. And today we can only have an influence or an impact playing with the different permeability degrees of the cork. Copper has an effect. It allows us to delay the formation and the release, but it does not avoid it. And oxygenation today, except for in the fermentation, it is not a solution. We can offer a normalized test to measure all this, and we're working in order to develop remediation, more effective remediation measures. And this is my team. Thank you very much.